Okay, good evening everyone. Today I'll be presenting a complete overview of Arduino and its role in industrial integration. My goal in this presentation is to bridge the gap between basic microcontroller programming and real-world industrial automation such as sensors, actuators, communication networks, and safety systems. Before jumping into the industrial side, I want to acknowledge that Arduino actually started as a beginner friendly prototyping tool. People used it for learning electronics, building hobby projects, experimenting with sensors, and creating prototypes. Over time, it has evolved into something much bigger. Even industries have started adopting Arduino's higher end boards because they offer reliable hardware, powerful processors, and compatibility with the industrial voltages and protocols. This presentation also includes some foundational topics uh, that are like Arduino IDE setup, the basic structure of Arduino program, understanding data types and variables, purpose of operators, loops, functions, strings, array, time-related functions. These basics are essential because these are kind of like the programming backbone of all the advanced industrial concepts that we are going to see in this presentation. So, firstly, I'm going to start off with the Arduino IDE installation. To begin with Arduino, the very first step is installing the Arduino IDE. The IDE stands for Integrated Development Environment, and it's going to provide us with everything we need to kind of write, compile, and upload code to the Arduino board. After downloading it from the Arduino website, you follow a simple installation wizard. So basically, you choose your board, allow USB drivers to install, and then open the IDE. Once it opens, the first thing we do is select the board we are using. Usually it's a Arduino Uno or Nano. These are the simplest board. And then we choose the correct COM port. This configuration allows the code to be transferred into board's microcontroller. So basically what happens is the Arduino Uno is the most common board which is used for academic projects. It is based on Atmega 328P microcontroller. This microcontroller has different memory sections: flash memory for storing a program, SRAM for variables and runtime data, and EEPROM for long-term storage. It has various peripherals built in: timers, PWM generators, ADC converters for analog inputs, UART for serial communication, I2C, and SPI for sensors communication interrupt pins. Understanding this architecture helps us, appreciate how later industrial boards take these features to a more reliable and a rugged environment. See, every Arduino program has two main sections. First is the setup, and the second is the loop. This runs once the board is set up. The setup part, it's just going to run once when it's all started. It's used for initializing sensors, setting pin modes, and starting a means of communication. The function runs forever. It's similar to the heartbeat of the controller. Everything the machine needs to do continuously, like reading sensors, checking inputs, etc., etc. The simple structure makes it very easy to expand small projects into large modular industrial code bases, like data types, variables, constants. A very important part of programming is selecting the correct data types. Arduino supports integers, floating point numbers, characters, Boolean strings, long integers, unsigned integers, and more. Choosing the right type improves memory efficiency and prevents, data overflow. Variable holds information like sensor readings, motor speeds to make programs safer. Constants are used for values that should never change during execution, like pin numbers, threshold temperatures, or motor limits. In Arduino programming, operators allow us to perform calculations or logical operations. There are arithmetic operators, logical operators, comparison operators, without operators, decision making logic. An automation system, which if it wouldn't exist, it would have been very one dimensional functionality. There are also loop and control statements. There are if else loops, switch cases, brake control, program flow. All of these are very essential for basic functioning of the microcontrollers and all of that stuff. Then there are function strings, times, array. Function break large programs into small manageable pieces. String help handle text through an embedded system. We prefer character arrays to kind of avoid memory fragmentation. Arrays store multiple values. Time function like milli s bracket help us implement non-blocking code, something extremely important in real-time automation where delays can cause accidents. Now going on to the next page. Here it is. So basically here, this slide kind of gives a comparison between two categories of hardware. First is the prototyping boards and the second is the industrial boards. On the left, as you can see, there is Arduino Uno or Nano, which operates on a 5-volt logic and uses Atmega 328P processor and are perfect for, classroom or hobby level experiments. They work well in non-harsh environment where noise levels are typically low and precision requirements are moderate. On the right hand side, we can see industrial boards like Arduino Potenta or Arduino Opta. These are built using ARM Cortex M7 or M4 processors, which are more powerful and support multi-threading and advanced control logic. So these boards typically use 24 volts logic because factories are full of electromagnetic noise from motors, relays, and heavy machinery. The heavier voltage ensures that the signal remains stable over long cable distances. The environment specification is also different. Industrial boards are built to withstand temperature swings, vibration, dust, and sometimes even moisture. These are rugged to survive years of continuous operation. This comparison, kind of helps us understand why simple boards are not suitable for industrial automation without additional protection because they would just simply kind of wear off. Coming on to the next page. So here in this page, we have the Harvard level architecture model, which is used by microcontrollers in Harvard architecture program memory and data memory, which are physically separate. This kind of prevents a situation where data accidentally overrides instructions, something that could be catastrophic in industrial systems again. This structural advantage makes microcontrollers more predictable and more reliable. On the right side, we see two development environments, the standard Arduino IDE and the Arduino PLC IDE. So the standard IDE is great for individual scripts, learning and prototyping, right? It uses C++ syntax, and the Arduino PLC IDE on the other hand allows us to write programs using industrial language like ladder logic or function block diagrams. This is extremely useful in factories where technicians already are kind of aware with PLC programming, right? Now going on to the next page. Yeah. So this slide is kind of, has a purpose of making us aware with industrial coding standards, and it kind of explains the difference between a hobby style coding and an industrial coding, like what is actually used in the industry itself. Hobby code often works fine on a tabletop project, but it may fail on a machine due to ambiguous variable widths, timing issues, or compiler optimizations. In industrial coding, we always use fixed width types like UINT 16 underscore T or INT 32 underscore T to ensure exact memory usage. Right. Constants are defined for safety parameters, and the volatile keyword is used to inform the compiler not to optimize certain variables used inside interrupts. These standards ensure that industrial codes is behaving in a predictable and testable way, reducing the chances of malfunction. So going on to the next slide. Now we have a industrial state machine and its implementation. So in this slide, there is a structured way to control the sequence, which is clearly visible here. To control the sequence of operations in a process, the state shows here are idle, filling, heating, and discharge. Each state has a specific condition that determine how the machine transitions to the next one. On the right, we can see the implementation using a switch case block, which builds on our earlier discussion of how control statements operate. State machines reduce complexity by breaking the systems into smaller parts, manageable states, but most industrial equipment from bottling plants to conveyor systems is built using this concept. So this entire cycle, this entire implementation is kind of, a demonstration of how the industrial level applications work using advanced Arduino boards, not just the Arduino Uno or the Arduino Nano. These are hobby level projects. Coming on to the next part, which is clean code practices. So this slide is particularly for, displaying a modular architecture. The main loop is treated as a conductor, coordinating the flow between input reading, processing, and actuation. This prevents the code from becoming messy or entangled, right? Unit testing and isolation ensures that if a sensor fails, it doesn't crash the entire machine. Industrial reusability means writing functions that can be used for multiple machines or sensors, making the code scalable and easier to maintain. This slide shows how simple practices like functions, arrays, and non-blocking structure can come together to form, a clean industrial code. Coming on to the next page, which is memory management. So one of the biggest challenges in embedded systems is managing memory carefully actually. This slide introduces the concept of circular buffer, as you can see on the left, which is continuously used to store new data and overwriting the oldest data when the buffer becomes full. Right. So there is no concept of, cache being so much full that the system can't accept any new data. But this is used in applications like data logging, serial monitoring, and communication. And on the right side, we can see serial data parsing methods and warnings about using the Arduino string class, which can cause memory fragmentation. Instead, character arrays and pre-allocated buffers keep the system stable. This connects back to the earlier topic of arrays and strings, showing how they are used in real-world memory management. Coming to real-time responsiveness, if you see, this slide demonstrates the problem caused by blocking code, especially the delay function. The delay function is used when the system becomes kind of unresponsive for that duration, which is extremely dangerous in industrial equipment because emergency signals might be missed and it might cause a catastrophic situation, which can be very harsh and which can be, something of great repercussions. The solution is cooperative multitasking using milli-s function. This method allows multiple tasks to run independently without blocking each other. This is essential in machines where you must simultaneously monitor sensors, update displays, communicate via Modbus, and respond to emergency stops so that nothing is missed out at least. Now, coming off to algorithmic control, this slide compares two control strategies, bang bang control and PID control. Bang bang control is simple. It turns things fully on or fully off. It's useful for basic system but causes overshoot and oscillation. PID control, however, adjusts the memory smoothly using proportional, integral, and derivative components. It helps maintain temperature, pressure, or speed within tight limits. PID is used everywhere in industry, from injection molds to conveyor belts. Coming on to the next part. Here there is interrupts and hardware level response. This slide shows why interrupts are crucial in automation. For example, an emergency stop button must be detected instantly without waiting for the loop to run. Interrupt service routines allow the processor to pause everything and respond immediately. The second example shows that high speed pulse counting using encoders. These sensors send pulses too quickly for the normal loop. So interrupts ensure accurate and timely counting. Now there is field bus integration.